Most LTR failures are feature failures, not model failures. SHAP makes the broken ranking signal visible before it ships. This is the workflow you'll know how to run when we're done, which trains the ranker on your cases and flags leaky promo signals with SHAP. I'm Professor Pi, teaching search and IR with simple Python. Feature bugs often hide inside the signals we hand a ranker. You can get great validation numbers and still be promoting the wrong document because one feature hijacks the score. Spotting that by eye is slow and noisy. SHAP gives per document, per feature attributions, so you can see exactly which signal is buying exposure. At a high level, we want to train a tiny ranker and then ask SHAP why it ranked what it did. The objective is to find a leaky promotional signal, for example, a clicks feature that only correlates with relevance for a single query, and then measure how much exposure changes when we mute it. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves different. We start by creating a tiny labeled table that mimics 2 queries and 3 documents each. This snippet assembles a tiny relevance dataset for 2 queries in pandas. We build a data frame named pairs, so every row binds a query ID and doc ID with a graded label plus 3 interpretable ranking signals. The BM25 column mimics lexical relevance, clicks captures behavioral bias, and dense offers a semantic score, so later steps can stress hybrid retrieval. Because each query repeats 3 times, the toy dataset already carries proper group structure for learning to rank without extra joins. The printed preview confirms the first 2 rows align with the intended query and label ordering, showing the data is coherent. Now, we need a quick check to see which features follow the labels inside each query. This example inspects how each feature tracks the labels within a query using pandas group by math. We reuse the features list to compute Spearman correlations, so we can spot inversions even in 3 document groups. The resulting chorus frame exposes that query 1's click signal fights the graded labels, while BM25 still leads query 2. Catching those dominant indicators early keeps us from trusting aggregate validation scores that might hide failure pockets. The printed dominant signals dictionary points straight at the feature that now deserves deeper investigation for each query. Finding a suspicious feature is one thing. We now train a ranker to see how that feature affects predicted exposure. This code trains a LightGBM LGBMRanker on our pairs table and surfaces a leader per query. We compute groups, so the lambda rank objective receives the correct document counts per query. The ranker fits on BM25, clicks and dense, returning scores that we cache in the score column for later diagnostics. Sorting by query ID and score reveals which documents would be exposed first under this model. The top doc scores output names each winning document with its rounded score, making it clear whether the suspect clicks feature is already skewing exposure. Once the model shows a surprising top document, we ask SHAP to explain that decision in feature contributions. This snippet uses SHAP's TreeExplainer on the LightGBMRanker to audit the misranked document from query 1. We instantiate the explainer with our trained model, so it replays tree paths and returns SHAP values aligned with the feature ordering. Because SHAP may emit a list from multi-output models, we guard against that and wrap the resulting array into SHAPDF for convenient filtering. Selecting the row for doc ID B and rounding brings each feature contribution into view, highlighting which signals push its score upward. The doc B SHAP dictionary makes the culprit obvious by quantifying how strongly clicks drive the unexpected ranking. If clicks is the culprit, we want to see exposure when its contribution is removed. This example simulates dropping the risky signal by reconstructing scores without its SHAP contribution. We read explainer.expectedValue, coerce it to a scalar, and remove the suspect column from SHAP df before summing the remaining contributions. Writing those adjusted scores back into pairs and re-ranking lets us compare each leader against the earlier top scores dictionary. The comparison dictionary reports both the original and adjusted winners, so we can see how exposure shifts once that signal is muted. The feature drop shift print, therefore, tells us exactly which query flips rank after suppressing the problematic feature. If you wanted to map this tiny example to production, you replace the toy pairs with your real impressions log, keep the same feature audit steps, and run SHAP on a held-out slice where you suspect leakage. The pattern is identical and scales because TreeExplainer summarizes tree logic, not raw sample size. Recap: you now have a compact workflow. Train a small ranker, use SHAP to attribute per document scores, and check whether a single signal is driving exposure for some queries. Use this when you suspect one feature is monopolizing exposure for a subset of queries. Remember the caveat. SHAP explains the trained model, so both model bias and data bias show up in the attributions. Next step, try muting a different feature and measure how many queries flip their leader. Or scale this audit to 1,000 queries and track the flip rate as a metric. If short, practical IR helps, subscribe and watch the IR videos.